record.
It's like a 8 times 1
Just guess 50%. Times 8.
It's not 50% times 8. 50% times 8 is 4. So that would be a 400% probability she could guess 8 out of 8 right. That probably doesn't feel all that great, right?
4, right?
No, it's
It's 0.5 to the 8th power.
0.5 to the 8th power, which is pretty small number. Yeah? Okay, so we were comfortable saying that the answer was yes because of a low probability. Everybody good? And so a huge component of statistical reasoning is that pretty much all of statistics is based on using probability concepts to make decisions. Okay? So, it's using probability to make a decision is not that hard. If something's really unlikely to happen by chance, it's probably not by chance. And then we can say something else. Okay, we can make a different conclusion. But finding the probability that something happens can be quite complicated. Okay? So the bulk of you're not going to have many questions in which I'm like, okay, I have 10 marbles in a bag and there's a red one and a blue one and 2 green ones and blah, blah, blah. And what's the probability I pull a green? Okay? The probability questions you guys are going to be asked to do are going to be way more complicated than a typical probability question. Also, who cares about marbles coming out of a bag? So we're going to talk about chance events, but when we talk about chance events, I don't want you guys to associate chance events with just, the probability tools like spinners and dice and everything else that Ms. Meister has up here. You guys get what I'm saying here? Okay? But rather, these are tools to help us calculate more complicated probabilities. Okay? So, an example of a chance event. Does anyone know it's going to rain today?
Yes.
Maybe. Is it an easy question to figure out the probability that it does rain today? Is that an easy question to figure out?
Yes.
Well,
Science.
It's not.
You look at the weather app, so the science behind the weather app, someone had to come up with it. Was it easy to do so?
No.
And how do they do that?
Looking at
Weather around us.
They look at the weather around us. When they say there's a 50% chance of rain, what are they really saying?
50% of the area was.
I don't believe that's true. 50% of the time in previous years, with similar conditions, it has rained. Start getting that vibe, yeah? How do you that probability is incredibly complicated, and believe it or not, okay, you almost have to go to school to do just calculate those probabilities. In fact, that's what weathermen do when they go to school and study meteorology. It's like a whole branch of science to try to predict the weather based on the current conditions and what the conditions are going to be. Okay? You guys, you want to know another probability event? How many red lights am I going to hit on my way home from work today? You with me? That is the chance events that we really care about. What's the probability of rolling a 2 on a die is not something we care that much about. That doesn't mean we can't use die to model real-world events. Good so far? All right, so I want you guys to envision a contest from Coca-Cola that says you buy a bottle of pop, you open up that bottle of pop, and underneath the cap it says, hey, you're a winner. Or try again later. Now, in modern day, they give you a code that you put in to a website or something. But can we envision this contest? Okay? And Coca-Cola has said that the probability of winning this contest is 1 in 6. Everybody good so far? We have this vision of what's going on. And what we're going to do is we're going to take 7 of us. We're going to walk over, me and 6 of my friends. We're going to walk over to Speedway. Everybody's going to buy a Coke. We're going to turn and see if we won. Everybody good? So 7 people, me and my 6 friends, are going to go buy a Coke. How many of us would you expect to win?
At least.
One, maybe two. Well, yeah.
We would expect 1, and you guys are saying maybe 2. And talk to me about this maybe 2.
Because there's 7, 1, 6. So the 7th person could be the.
So you would expect 1 of the initial 6, and then the 7th person could or could not be a winner. Okay. On average, do you think we're going to have a lot more than, a lot less than? What do you think?
I think it's going to be pretty accurate.
Okay. So if we walk over there and 3 of us win, would that be surprising?
Yes.
Kind of. Not fair.
It's kind of surprising, but not very. Is that the consensus? Kind of surprising, but not very.
I think it's very surprising.
3 out of 7 wins. Kind of surprising. Seth thinks very surprising.
I like pretty surprising better.
Pretty surprising.
Fair.
Fairly surprising. Moderately surprising. Okay. You're ridiculous. Approximately surprising. Why is it surprising again?
Only 1 in 6 wins.
Statistically.
Oh, don't use words that you don't know how to actually justify yet.
What was
We
given by
expected 1 and we
Coca-Cola?
got 3.
The statistical
You
probability
expected
of winning
1 or
is 50.
maybe 2 people.
We'd expect 1, maybe 2. And so when we say that something is surprising, what does that mean for us to be surprised by something?
We didn't
The
expect
outcome
We
it.
didn't expect it.
Based on.
Okay.
There's a low chance of it happening.
Okay, so a low probability. So if I were to ask you guys what is the probability that we get 3 out of the 7 people to win, how would you feel about that? Calculating that probability.
Maybe.
Maybe, what is it?
It's 20% for each person, right?
Nah.
No. Or, oh, wait, no, not 20.
Yeah, but see, so here, let's go through all the things we would have to think through, right? So, 7 people, we are 7 people right here, right? And so we could figure out, for instance, what's the probability I won, Seth won, Teddy won, and then the rest of y'all are losers. Okay? We can figure that out, right? It'd be 1 in 6 times 1 in 6 times 1 in 6 times 5, 6 times 5, 6 times 5, 6 times 5, 6, yeah. And that feels like a pretty good way of figuring out what is the probability of getting 3 or more winners. What's the problem with just doing that? That finds the probability that we are the 3 winners out of the 7. But we would have to not, it could be, you guys are the winners. Or you guys. Or you guys. You guys see what I'm saying? There's lots of different ways this could happen. So all of a sudden, we're starting to have a really complicated probability. And I don't know about you guys, but I don't want to do this by hand. By the end of the year, or by the end of November, you guys will be doing this by hand, but we're nowhere near ready yet. Okay? So how do we decide what is surprising? We have to ask ourselves two questions. You said it's surprising when it's unlikely to happen. How unlikely does something need to be for it to surprise you that it happened? Less than 15%? 50?
What? That's not likely.
Okay, dude.
So.
Dude.
has to be on next.
Would you be surprised if I spun a white on this?
Yes.
If you predicted it beforehand, then you're.
Would I be surprised if you spun the white? Yes.
I didn't.
I'm not surprised.
I'm not surprised. I'm surprised.
Would you be surprised if I flipped a coin? I got 2 tails and 1. If I flipped 3 coins, I got 2 tails and 1 head. Is that surprising?
Barely.
You're paying my bucket.
No, but like actually, like if it's less than like,
It depends on like if you predict, if you're predicting it.
then it is fairly surprising.
Stop being a lot.
I feel like it's like the
Would I be shocked?
the idea that you take
Well, this is
beforehand.
okay. Shocked.
Shocked.
Would it be like, wait, how surprising? What probability would make you stop and say something isn't right here? Is that a better way of describing
I
it?
like that.
90%?
No, that's not what I said.
How unlikely does something need to be before you're like, hold up?
19%.
19%? 5%?
I said 490.
Okay. 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 So, when we have complicated probabilities, one thing we might do is create something called a simulation to calculate the probability instead of going into the theory behind it. Okay? So, do any of you know the probability of getting 3 out of 7 winners? Okay. Neither do I. I haven't calculated it. I can figure it out, I suppose. So what we're going to do is simulate. When we say simulate, we take a known chance event and apply it in a new situation. So, you guys, can you think of any probability tool that can help me simulate a person opening a bottle of soda, in which the probability of winning is in fact 1 out of 6? A die. And in fact, I can roll that die. I got a 4.
Yeah,
Did I win?
No.
Well, which one is
One.
It's gotta be this.
I think we're setting it.
Well, so technically we have to state what it is first, but I set this up so I can make this fun. If you roll a 1, you won.
Nice.
Okay? So, hold on.
Oh!
Boom!
She
I got a
won.
3 pop, guys. This time I didn't. Everybody roll one of your die. Did you win? Did anybody win?
I did.
Second roll.
Hey, I see a 1 in my back.
Hey,
I got up to 8.
Just not roll.
Everybody good?
I won.
What do I need to roll?
A 1. If you roll a 1, you won a free
I
soda.
got it first try.
I got it.
You must be really good at opening
I'm
soda.
surprised with that, Teddy. I'm shocked.
Okay.
And it's
Alright. So, here's what we're going to do. We don't want to simulate one person opening soda. We don't want to just say, did you win or not? We want to know, how often could we get 3 or more winners? So, what should we do? Instead of rolling 1 dice for 1 soda, we should roll 7 dice for 7 sodas. Now, guys, I'm recording this, so I would like you to please stop doing this for a second. I'll pause the recording for the people at home. Could you please stop touching the dice? And just put them down so people can hear what I'm saying to explain what's going on. Please and thank you. Okay, here's what you are going to do. You're going to roll those 7 dice. You're going to write down how many people won, quote unquote. In other words, write down how many ones you got. Yes? All right, let's see. We got 11 of you, so I would like each of you to do this 9 times. Okay? Don't look at me like that. When you are done, we're going to make a dot plot. To make said dot plot, we're just going to have to be patient. You are going to put stickers for each number of winners you have. So how many stickers are you each putting on this dot plot? 9. I would like you to use green stickers for anything that is 2 or lower. I would like you to use red stickers for anything that is 3 or higher. Do you guys understand what I'm asking you to do? Does anybody, those of you at home, I'm going to pause the video so that you do not have to listen to the multiple rollings and rollings and rollings of the said die. And I will send you a screenshot of the, yeah. Okay, so here we have our dot plot. And as you guys can kind of see here, what I intended to do is give you guys like the red to kind of say, hey, if someone could get 4 or 5 by chance alone, then 3, that's more support that 3 is possible to get by itself, yeah?
Yep.
So, what happens here is we kind of have 2 things going on. We definitely got, in the what is actually true, the 7 people who actually went and get the soda pops, right? Okay. We expected 1 and we got 3, right? So we got more than expected. Is everybody with me? And in my head, there are 2 explanations for how we could get more than expected. Does anybody want to guess one of those 2 explanations? Luck. And if that's the case, the actual probability is still 1/6. You guys with me? What's the other explanation? The probability is incorrect. And if that's the case, what can we say about the probability? It's bigger than 1/6. So we're going to kind of operate in this world of when it comes to making decisions, we got to decide which one of these 2 things is the right explanation. Cool? And to do that, we're going to use a probability to make said choice. Okay? When we did this, which of these explanations was true? Luck, right? The probability that we used was 1 in 6 because you rolled die, yeah? All right, and the question we need to ask ourselves is, what is the probability that we get 3 or more winners? Now, how many times did it happen? We just count. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It happened 11 times. And if I asked you how to write that as a probability, well, you guys did this 9 times each, right? And there's 11 of you. And then 99, except for Miss Meister did 1 trial of it. 2. Okay? So what is the probability that we got 3 or more winners? 11 out of 100. Now, is that the exact probability? No. Is it close enough? Yeah. Do you think it's close to what the actual probability is?
Yeah.
Okay, so when you guys first learn about probability, you're given die and you're allowed to play around with the dice or spinners or coins or whatever, right? So you still do. We're still going to use those things, but you notice I didn't ask you a single probability about the die. That's boring. But using it as a tool to find another probability through a simulation can kind of give us some other ideas. Okay, so this is called a simulation. How could I make it better and more? How could I do this so that it would be closer to the actual probability? Just make you guys do it a lot more. Okay, and in fact, the more we do it, the more and more and more it's going to resemble the actual probability of getting 3 or more winners in this particular scenario. Cool? All right. So, talk about simulation. So, many probabilities that are like reported out and stuff like that are in fact simulations because sometimes we don't know all the factors of what's going on. Okay? So let's go ahead and say I want to choose a simple random of 6 from a group of 60 seniors and 30 juniors. The group I get is 4 juniors and 2 seniors, and the seniors are mad. Yeah? Are they justified to think there's something wrong with the sampling process? Maybe. Could I just get a random sample that worked out that way?
Yes.
So if I want to know, should they be mad at me for getting that sample? Shouldn't I figure out the probability we could have gotten such a lopsided sample? So what we're going to do is design a simulation to decide, is it possible that we could have gotten this lopsided of a sample by chance alone? Because, like, you wouldn't want to get mad at somebody for doing something that was just random chance. Cool? So how would you do it?
Put 60 green marbles, 30 yellow marbles in a bag.
Do you have that? We're actually going to do this simulation, so do you have that?
I just said create one, not one that we could do.
Divide by 10?
Take 0.6 of a marble.
Oof. What would the actual process for gathering a sample of 6 people from 90 look like? Well, and if I asked you to describe a process to gather said sample, what would you say?
Number all 90 and then randomly generate.
Assign each person a number, yeah? So we're still going to assign each person a number. We're not really worrying about who's juniors and who's seniors when we gather the sample, but when we assign these numbers, you guys, let's assign the seniors 1 through 60 and assign the juniors 61 through 90. And wouldn't that give us the equivalent of numbering 1 through 90? Everybody good? All right. After we assigned everybody a number, what would we do next?
Use a random number generator.
To get 6 unique numbers. And they'll be my sample, yeah? Now the question is it weird to get a sample of 4 juniors and 2 seniors, yeah? So here's what we're going to do. For the simulation component of this, we're going to record the number of quote-unquote juniors. So, guys, take out your calculators. You're going to hit math. You're going to arrow over to PRB just as a reminder to get to that random digit generator, okay? You're going to choose option number 5, the random integer. And we want to generate digits between 1 and 90. And just for fun, we're going to generate them 6 at a time. If you end up with 6 when there's repeating within those 6, we'll ignore that time and generate 6 new numbers.
Is random integer no rep a way to do it without having to worry about that?
Does yours have that?
Yeah.
If yours has that, you should pick that. Mine doesn't have that.
Oh. Nice.
Oh, it does. Oh, mine does have, it's number 8 for me.
Oh, that's nice. The newer operating system must have it. The old one, I don't think. Does yours have something that says rand int no rep?
Yeah.
No, it doesn't.
Mine
Do does your app have an update?
I mean, no, this thing's a P. Doesn't have stuff. Yeah. I'm more upset. I've been teaching statistics for 10 years and having to ignore repeats. And I find this frustrating to know you could do this How did I not know about this? Because I literally do this all the time. And how in 10 years has not a single student brought this up to me?
Because it's landed. That's
Well, I was literally just thinking, there's got to be a way to do this. And I looked down and I was like, wait a minute.
That's crazy. Anyway, go ahead and generate your digits. And guys, looking at my sample up here, how many juniors do I have? 2?
87.
How many do you have?
2, 2, 3.
I got 90.
So you guys catch my drift on this? So we're going to calculate this probability.
I got 90 and 1. Nice, bro.
You guys, that's really surprising to get 90 and 1. All right, what'd you have? How many juniors?
2. 1.
2.
3. 2.
1. 0. 2. 1.
Okay, cool.
1.
All right. So what's the probability so far? What's our probability of getting 4 or more juniors? 0 out of 11. Yeah? Do it again.
I got 3.
2.
2.
3.
Still, it looks like 0 out of 22. I'm 20. I only did 1, but not both. So 23. If I needed to, could we figure out how many dots are on here?
Yeah.
Just count them. Yeah. One more time.
Three. 2. What? 1. 0.
2.
3.
1. 2.
3.
So you guys, can the seniors call shenanigans? Can they say that something improper was happening with the way this sample was gathered based on this simulation?
Yes.
Why?
Because it's a simulation.
The simulation shows it would be very surprising, very, very, very surprising to get 4 or more juniors. Everybody good? So, here's the deal. When it comes to this concept of simulation, I'm going to expect one of 2 things from you guys, okay? The first one is, if I give you the results, whether it be like this graph or the previous graph, right? If I give you a graph of the results, can you figure out what the probability is? How many of you guys feel comfortable using this graph to find the probability of 4 or more? Or this graph, finding the probability of 3 or more? Do we feel okay? Finding the probability from a graph. Okay? The other thing I'm going to ask of you is to kind of decide, is a simulation a good simulation, why or why not? So, if the probability of winning a soda was 1 in 8, should I be using a dice to model it?
I don't think so.
Not 6.
Not a 6-sided dice. Well, you think I should use an 8-sided dice?
Does that exist?
Does it exist?
It does.
You mean like
It does.
this?
Yeah, no, it does.
Beautiful 8-sided dice. Technically, this is an 8-sided die. The singular is die. The plural is dice. Yes, if you were interested in having all these lovely dice, you could in fact order a pound of dice from Amazon.
4.
I just don't understand why it has to be a pound.
For how much?
I don't know. We should look it up.
How many die in a pound of dice?
I can give you a ballpark estimate. Okay. You know what? I think we're at a good place to take a break. So let's take a.
2 answers.
All right. This time, we're going to simulate a different question. All right. So in this scenario, we've decided that the sampling method, there's something wrong with it. So here's what we're going to do. We're going to take that bin with all the names in it, and I don't want to have to empty out all the names of these people, separate out into seniors and juniors. So here's what I want to do. I'm going to generate, I'm just going to keep drawing until I get a sample that has 4 seniors and 2 juniors in it, so that it is a representative sample. And my question is, what is the probability it takes me 10 or more tries to get that amount of names? Do you guys get what I'm saying?
What is the probability?
Anybody else feel slightly like...
I.
What do subs grades look like?
I have immaculate grades.
Sev?
So, guys, what's our question of interest here? Like, as we go through, let's go through, if I go to do this, first of all, should I be generating 6 at a time this time?
No.
No, because, like, how do I simulate drawing my first person?
1 in 9.
1 in 90, yeah?
But doesn't doing it with no repetition do that?
No. Yes, but no.
You have it.
I'm sorry?
You had the no repetition.
Did I really?
Yeah.
It's at the bottom.
Lolo. How long have I been teaching stats? Since you've known me, right?
Yeah.
Did you know I can do a random integer without repeating? Like, look at this option.
So great! I just sent an email to the whole staff. Your grades are good. You do not need to bring your laptop to me. I said, if you do weighted grades, you have to bring me your laptop. I just checked yours. Yours are good. Thanks, but I'm so
You just
excited about
insulted me.
that calculator feature. Glad you'll be able to sleep tonight.
So crazy.
So exciting.
She's insulting you.
Blake Harville deserves some candy.
No,
Who's
no,
landed?
he does not.
I figured out that she.
You guys, if she's insulting me, I deserve it. Because you know how much more frequently I insult her than she insults me.
Your sweater too?
Isn't it cute?
It's adorable.
It's got a little Halloween vibe, yeah.
Totally. Perfect fall vibe. Okay, bye.
She can't be 10 feet off. She has to come from
I'm going to go ahead and generate my random integer. So, when I generated that random digit, I got a 14. Did I get a junior or a senior?
Got a senior.
Senior, because remember, 1 through 60 was the seniors. And 161 through 90 is the juniors. And you guys, the reason I don't want to do 6 at a time is because I don't know if it's going to be 6. I don't know how many I need to generate. You with me?
Because why?
So in this case, I got a senior, right? Let's do it again. I got a senior. My next person is a junior. Next person is a senior. Next person is a senior. Next person is a senior. Do I have the sample I need yet, even though I've drawn 6 times? No, so I got to keep drawing. So this is why I didn't want to do 6 at a time, because you have no idea how many you're going to need to draw.
But why can't you just draw 6 until you get 42?
So are you saying once you draw the 6 people, you're not putting it up?
Correct. So I don't think I had any repeats. Did I have any repeats? Yeah, I didn't have any repeats. Okay, so in this particular case, how many draws did I do?
10.
10. So I could be, that particular one was this dot. Now, could we do this again? Am I going to get 10? Maybe. If I did this a bunch of times, I'm going to get a different response each time, yeah? And that's to be predicted. All right, so what is the, what are we recording in this particular case? So we still have the 1 through 60 being the seniors, the 61 through 90 being the juniors. We're going to use a random generator without repeat. And what are we recording? We're recording the number of generated numbers. And that might feel a little bit weird. All right, and the goal was, what's the probability it takes us 10 or more draws? If I gave you this graph and said, if I gave you this from here and said, what is the probability of 10 or more? What would you say?
11 out of 50.
11 out of 50? Because there are 11 dots that are 10 or more and 50 dots total. So we had a similar context here, but because the question was different, what we recorded from this context was different. And so we need to be paying attention to that kind of stuff. Now, there was a time, maybe 3 or 4 years ago, no, it was longer than that, there was a probability question on the AP exam that kids could not figure out how to do. It was a really hard question. They set up a simulation. Some kids set up a simulation and got credit, even though that's not what the College Board wanted them to do. They set up and ran using random digits on their calculator, and they actually got full credit for it. Just as a heads up. Cool. All right, next. Some basic probability rules. Okay. An event is a chance process, any chance process. But again, I want you guys to get away from thinking chance processes are dice or coin flips, and I want you to start thinking about chance processes as real world events. The weather. If I go to the bathroom right now, is somebody going to be in the bathroom stall? What's the probability? You guys see what? There's all sorts of chance events that happen all the time. Okay? An outcome is a possible result of an event. It rains is an outcome. It's not raining is an outcome. It's snowing is an outcome. It's sunny is an outcome. You guys catch my drift? All different outcomes for the chance event of today's weather, which, by the way, looks amazing. Doesn't it look like it's going to be a glorious day for the afternoon?
It's pretty warm out too.
Cool. Cool. Now, when I take this lovely 8-sided dice that I have, you guys, and I roll it, can you guys predict what it's going to land on?
A 2.
6. You guys are all wrong. All wrong. All of you.
That was my second guess.
Okay.
Okay, one of you.
One.
2, 3, 4.
None of you. All wrong again. It was a 5.
Okay, everybody guess.
8.
2.
No one gets to 6. You guys are really bad at this. Okay. You guys, are you with me that chance behavior, chance processes in general, are unpredictable in the short run? For a small number of trials, very unpredictable. Okay? Now, if I roll this 1,000 times, could you give me, give or take, what percent of the time I'm going to get a 1?
Yep.
And what percent of the time I'm going to get a 2? And in fact, if I asked you to draw a picture of what the dot plot of my rolls would look like, what would you guess?
Pretty even.
Flat, as we call it a uniform distribution. We'd expect exactly the same amount of 1s, 2s, 3s, 4s, 5s, 6s, 7s, and 8s, but they wouldn't be perfectly flat, most likely, but they would be like pretty darn close, yeah? Because chance processes are predictable over a long set of trials, or in the long run. So what we love about probability is that in the short run it's unpredictable, which means, like, I don't know, assigning treatments, all that kind of stuff. You can't predict who's going to be in what treatment group. It's a great way to do it. But in the long run, you know that you're going to get about the same people in each treatment group. Everybody good? So the last thing we're going to talk about today, the world's most basic type of probability on this 8-sided dice. If I ask you, what is the probability I roll either a 1 or a 2, you would say 25%. How are you getting that 25%?
2 over 8.
You did do 2 over 8, and why 2 over 8? You do your desired outcome over your total number of outcomes. And if only all probabilities were that simple. But alas, we're going to spend the next month talking about all the different probabilities and results of chance outcomes. Whew. You guys, I'm exhausted. Aren't you tired?
I think we're done for today. Yeah.
You are done for today. Unless
Where did female come from?
that, oh yeah. That, you guys, that's license. This used to be a different example, and I obviously didn't change it all the way through.
There she is.
Uh-oh.
you notice anything about the
Yeah,
ceiling?
there's anything different.
Oh.
No. I believe you should give that to Blake. Because he's the one.
No, I believe it because it turns out he did this in my room as well.
And I wanted to know if you felt like it was appropriate for teachers to give kids distracting toys.
Oh. Only if they win bingo.
Where are these in physics? Blake, get that down, yeah?
It normally falls down on its own after a while.
It's been a little bit since it's been up there.
Wow.
Whoa!
Do you remember the year I had the flingy
Yes.
things that stuck all over the ceiling?
Yes.
Wait, I just said, does this mean I can give you a hard time? Because that's really a hard time.
Yeah, definitely.
That's all I
Okay, that
got.
was it.
That was it.
Would you like some of those?
Yes.
Yeah.
Oh,
I could always pay you back. I could just bring them in here and start throwing them around.
You wouldn't even need to. You know I have all this kind of crap in here anyway.
But no, I know.
They
You
just
do.
don't know about it yet.
Sorry, little thing. I was wondering where he was, and I should have known he was probably in this class. So,
This is my squirrely group.
No.
squirrel 1, squirrel 2, maybe squirrel 3.
No, definitely. That's the squirreliest.
No, I get it. And you know what? I think it's his shoes. He wears.
Those are the. I cannot wait for that fashion trend to go away.
Is it a fashion trend or is he just?
No, a bunch of them have those slip-on sandals, and I just.
They're called Crocs
No.
with
No,
socks.
those
Crocs.
Those are not Crocs with socks.
No, this is like a different brand name, and it's so messed up.
Those are Yeezy slides.
No, those are Crocs.
Wait.
Those are Crocs that are $50. I'm just teasing. Or maybe.
Those are more.
I know. All right. Have fun.
Sorry to interrupt your grading,
Yeah, that's exactly what I'm doing. The stack stuff like that. I'm working through it though.
but
Y'all have fun.
I had to give you a hard time when I could.
No, I know. That's fair.
Hey, remember that time? Now that I'm recording, if I ask you, are these two events independent from each other? What do you think? Unless you've done some calculations, you don't know enough information to answer this question. Have you guys done some calculations? Like, for instance, what calculations would we need to do?
Just the probability of New York or reading New York.
And
The probability of New York given the USA.
New York Times, given that you read the USA Today. Okay? We want to see, does knowing somebody read USA Today change the probability of whether or not they read the New York Times? Okay? All right. Now, hey guys, what's the probability of someone reading the New York Times?
15%.
Woohoo! What if I know they read USA Today?
14.2. 5%. Oopsies. My bad.
If I'm given that they read USA Today,
33. No. Isn't it?
I'm given that they are one of these people. So that would be 5 out of 35.
No.
So of the USA Today readers, what percent read New York Times? Everybody good?
Yeah.
And that works out to be about 14.3% because it's 5 out of 35 is 1/7, yep. Okay, so are knowing that we have those two percentages, now, are the events independent?
Yeah.
What's your scale for like how far apart can they be?
Well, what was the rule we learned yesterday?
They can't.
That the probability of A has to equal the probability of A given B. Are these two things equal?
No.
These are not the same value. So we are going to say not independent. Now, I bet that bothers some of you. Does that bother some of you?
Yes.
Why does it bother you, Landon?
Because they're so close.
Because they're so close. Right? So here's the deal. The way this works in the real world is we would probably if we wanted to generalize this to decide, is this difference significant from our sample, significant out of a sample towards a population, we have to do a whole lot of work to decide is it a significant difference or not. Okay? If we're only talking about this group of people, the sample from which this was taken, they are not independent because they are not the same. In the real world, what happens is no one would care about this without a broader perspective of generalizing it to a population. And there are statistical procedures you can use that we're just not ready to learn yet that can say, hey, is it reasonable that we would have seen this difference by chance alone? And the answer is going to be, for sure, it would have been reasonable. Therefore, we can't conclude a significant difference between the two. We haven't learned those procedures yet. So right now we're only speaking about this particular sample. And we're not saying there's a strong relationship going on, but there's something going on there. Okay? All right. So if they're different, for right now, if they are different at all, we are going to say not independent. Okay? Even if they're this close. That's okay. Okay. Now, for the next one, you guys, I'm going to make up something ridiculous. I'm using the numbers to prove some points about things, not to make up a realistic example, okay? So when I write this down, don't take it. You should take the data with a grain of salt, okay? Because I'm making it up for so that it has certain mathematical properties. Cool? Okay. So we're going to have a group of 40 people. We're going to ask them what is their t-shirt size. And then the possible responses will be small, medium, and large. And let's go ahead and say that the other variable we're comparing to t-shirt size is I want something to be, I'm just going to use the one I used last time, but it's a really bad idea. Laces and no laces on the shoes. The only reason it's a bad idea is L, and L can't be in both variables. But you guys are smart enough to figure this out. I believe in you, okay? Guys, sorry. Again, I'm trying to make this have certain properties. And I believe we have now reached those certain properties. Two questions I'd like us to answer based off of this two-way table. What was the probability of S? 0.25? You got 10 out of 40, which is in fact equal to 0.25. Yeah? Yeah, so if you would have done it that way, you would have found the probability of laces is 16 out of 40, which was what, 0.4? Yeah, 4%? Yeah, that makes sense. Okay, cool. And then S given laces was 4 to 16. So different fraction, same result. So this answer is yes. Whereas over here, oh, hold on. The probability of laces given S would have also been 0.4. Yeah? Okay, so for this question in general, they both get you to the answer yes, though with different proportions. Everybody good? Okay, so for the relationship between wearing shoes with laces and having small t-shirts is in fact independent. Okay, and if we do this over here on the other side, right, if we're talking about with mediums, the probability of laces given a medium t-shirt would have been 7 out of 25, yeah? Which is 0.28. 7 out of 25?
Oh, 25. No, never mind.
Everybody good? So I guess the point is with this particular thing, just because one t-shirt size was independent doesn't mean that all of them would be in especially if you have more than two responses. So if you have like a 2x3 table such as this one, it's possible that they're not going to just match up. Okay, next. So we said the small column is good and independent. Everybody good? All right, so here's my next question for you related to this. If I took out these, whoa. Whoa. No, let's just. So these columns were not independent, yes? Can you guys tell me what numbers should be there to make them independent?
Make it so it's the same. Fractions.
10 for medium with laces.
10 for medium with laces? And what was your thought process there?
You want 10 out of 16 to be the same as 25.
So you said 25 out of 40 needs to equal something out of 16, basically. And then kind of did some cross multiplying or whatever to get there. I agree. And if that's a 10, that makes this a 15, right? And then, let's see, if these two are 14, this would have to be 2 and 3. And now, do you guys see like the 2/3 and the 4 out of 10 and 10 out of 20? Like, do you see that relationship in the table? Okay, now, the other thing I want us to kind of think through is what would a segmented bar graph, you guys remember those? Okay, what would it look like if the two variables are in fact independent? So these are in fact two completely independent variables based on our table. We made them independent. Can we make a segmented bar graph of this to get a feel for what that bar graph might look like?
Should all look the same.
They should all, but like when we say look the same,
They'll have the same proportion of laces and no laces because,
so I'm going to sketch it real quick. So we have laces, no laces. I could sketch this the other way, I'm just choosing not to, because I also want you guys to see, it's a subtle but important distinction. So this is 50%, this is 100%, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, and so let's start with the smalls. What percentage are the smalls? 25%. And what basically we know is it's 25% laces or not laces. All right, now mediums were what? 62.5%? 10 out of 16 is 5/8 is 62.5%. Does that mean I draw the dividing line at 62.5%? No, where would I put it? Add on to the 25%. Because it's, so the total length of it is 62.5, and that'll put it like, I don't know, roughly here. 87.5, give or take. So notice the sections of those bars are not the same, but the overall distribution of those sections for both bars is the same, right? But they're not, it's not like 33% across the board. Everybody good? All right. Now, if you guys need to put this on the back of your paper, I will even give you some time because I know you probably are running out of space. There's one other major concept I want to kind of talk about here. And none of them are major concepts. Major misconceptions is a better way to describe what I'm saying. Major misconceptions that occur with this particular content. And so what I want you guys to do is find the probability of no laces and large t-shirt. This is an and question. You guys, what is the answer? Immediately. 0. Never happened. Everybody with me? Everybody good? It's 0 out of 40, which no matter, everybody good? Okay, next question. What does that mean?
Nobody.
Use statistical language about our two events. They are, begins with an M, mutually exclusive. If one event occurs, the other one cannot. Okay, you guys. Huh? What's stupid?
But they can't do that. It's just IRL.
In real life.
That's not right.
Statistically, it's right, but realistically, it's not.
As we talk about this as probability, this would include some sort of random selection from this group. If I'm randomly selecting from this group, what is the probability that that person is unlaced and large? 0. Okay, next question.
Wait, so.
Ah,
you're saying
ah.
this-
Ah.
If you do it.
What would we need to show?
Probability of no laces.
The probability of no laces, which is 24 out of 40? 60%? Yeah? The probability of no laces given large became is 0. Because it would be 0 out of 5, yeah? Now, if two events are mutually exclusive, that means one event occurring precludes the other one from occurring. The definition of independent is one event occurring changes the probability of the other event occurring. Are you guys with me that one event occurring rules out the other one occurring completely? That's changing its probability. So, a lot of times, students use the phrase mutually exclusive and interchange it with independent as if they are the same thing. Not only are they not the same thing, they are very far away from each other in meaning. Cool? All right, I'm done talking for today.